Hello, Luke. Welcome to Lesson 61. Today we're going to be talking about subsets and then subsets of real numbers. So let's get started. When talking about subsets, we need to refer back to a previous lesson when we talked about sets. So you may recall that if I have a bunch of numbers, let's say I have a 1, a 2, a 3, a 4, and a 4, and I ask you, what set do these numbers belong to? Well, your answer, hopefully, would be they belong to the set 1, 2, 3, and 4. End set. All right, so remember this is a set for these numbers, and we have certain notations that we use when we describe sets. So remember they have to be enclosed by braces, and we can't have a set that has multiple ones in it or multiple twos in it. Each one has to be unique. Okay, and there may be, in this case, 4 members to the set. There may be 1 member to the set. There may be infinite members to a set. Okay, all of those would designate different kinds of sets. Okay, so that's just a really quick review on what a set is. Today, let's talk about subsets. So there's a couple of pieces of terminology here that we're going to need to get through. So let's start with that, and we'll just kind of hit these one by one and work our way through. So first of all, and by the way, you should have your notebook open and ready, and you should be writing these definitions down as we go through. Pause the video if you need to. So first of all, let's talk about what a subset is. What's just the definition of it? And a subset is a set whose members are all members of another set. Now that may sound confusing. So let me give you a couple of sets. Let's say I have the set A. And set A includes the members 1, 2, and 3. All right? Then let's say I have a set, we're going to call it set B, and that is going to include the members, let's call it 1, 2, 3, and 4. Okay, so we have 2 sets, and if we look at the first set and its members and compare that to the second set's members, we see that all of the members from the first set are also part or contained in the second set. Okay, so this set has a 1, set B also has a 1. Set A has a 2 and a 3. Set B also has a 2 and a 3. So everything that is in set A is also in set B. So we would say that A is a subset of set B. And maybe I'll even say that here. Set A. Set A is a subset of set B. Okay? Everything that A has, B also has. It's really that simple. All right? That is what a subset is. Excellent. To add to that, let's take this one step further. The next definition here, we have what's called a proper subset. Okay? Now, a proper subset is simply a subset whose parent set has more members that are not in the subset. So again, may sound confusing when you just look at the definition, but let's look at an example. So if I have set C, and let's say set C is equal to 2 and 3. Okay? And then let's say we have a set D, and set D is equal to 2 and 3. Or actually, let's just make it look a little bit different. Let's make it 3, 2. Okay? So here we have 2 sets, and clearly set C is a subset of set D. Everything that's in C is also in D. Okay? So therefore, it is a subset of set D. However, it is not a proper subset, because a proper subset is a subset of another set, and that other set, the parent set we'll call it, has more members than just those in the first set. So in other words, these two, or C, let me go write that. C is not a proper subset of D. Okay? Now, I could maybe adjust this a little bit and say, what if set D also has a 0 in it? Now, is set C still a subset of set D? Yes, it is. Is C a proper subset of set D? Yes, it is. Because again, the definition tells us that not only does D have to have everything that C has, but it also has to have something else besides what C has. In other words, they can't be equal sets. They can't have, they can't be totally equal in everything. There has to be at least one member in D that's not in C. Okay, so here we would say, let me back this up now so we don't get confused. Now we can say C is a proper subset of set D. All right, so hopefully you understand that. And maybe just to throw this at you, I might ask you, is D a subset of C? Is D a subset of C? What do you think? Well, the answer is no. D is not a subset of C because D has a 3, 2, and 0 in it, and C does not have the 0. So everything that's in D is not in C. So therefore, D is not a subset of C, even though C is a subset of D. You following that? Same thing would apply up here. A is a subset of B, but B is not a subset of A, because everything that's in B is not also in A. You see that? So it's kind of a one-way street here. All right? Hopefully that makes sense. Now, we do have some symbols, or a symbol, that we use to denote subsets. So here I wrote set A is a subset of set B. Another way to say this would be to go A is a subset of B. So it's kind of the sideways U shape. All right. The sideways U shape basically reads is a subset of. All right. So this would read A is a subset of B. If I would have written it like this, we have to be careful. We'd have to read this backwards, and we'd have to say B is a subset of A. All right. So it does depend on which direction this U shape is pointing. We always start at the rounded side. All right. So A is a subset of B. B is a subset of C. Okay. Normally, we're going to read it from left to right. So normally, we would write it like this. A is a subset of B. Now, if I wanted to say, B is not a subset of A, and clearly it's not, we would write it like this. We would say B is not a subset of A. So we draw this slash through it. And the slash, remember, always indicates not. So B is not a subset of A. All right, so that is how we are mathematically going to denote subsets with symbols by this sideways U shape. Okay, so C is a proper subset of D. This is true. C is. Let's move on. Improper subsets. So an improper subset is basically the opposite of a proper subset. So a subset whose parent has exactly the same members and no others. So this would be kind of the way I began that second example. If I have A is equal to a set of, and you know what, let's just say it's a set of these symbols. Maybe it's a set of a smiley face and an exclamation point. There we go. That is the set A. And then the set B is going to be equal to the set exclamation point and smiley face. Okay. This would be an example of A being a subset of B, because everything that's in A is also in B. So A is a subset of B. This is true. But is it a proper subset? No, it's not, because they are exactly the same. They are equal. They are equal sets. So they are not a proper subset. And that's why we call it an improper subset. And the interesting thing about an improper subset is then it would always be true that we can also reverse these two. It's like a two-way street. A is a subset of B, and then B is also a subset of A. All right? So that is kind of the thing to note when we have improper subsets, is that A will be a subset of B, B will be a subset of A. You can switch those around, and it still will always work because they are equal in every way. Okay? Excellent. So that is proper subset, improper subset. Now let's talk about the null set, or the empty set. So this may seem a little ridiculous at first, but sometimes we do talk about the empty set. Okay? So, and when we do, we refer to it usually as the null set, but we will sometimes talk about it as the empty set as well. Either one, they are synonymous. So what is it though? It is very simple. It's just a set that does not have anything in it. There's nothing in there. It's the empty set. It's exactly what it sounds like. And it's usually denoted by these two curly braces with nothing inside. Or sometimes, as you see in the symbol here, it can be written as kind of a zero with a slash through it. Okay? Whenever you see that, that is denoting the empty set. All right? So when you think about it, is the null set, and maybe let's say a set that looks like this, 1, 2, and 3, and we'll call this set A again. So is the null set a subset of A? Is the null set a subset of A? Well, in order for that to be the case, remember everything in this null set has to also be in the A set. The null set doesn't have anything. So is this nothing in here? Well, sure, it's in there. You might not see it because it's nothing, but there is, a little nothing. Maybe I'll mark it as well, I shouldn't mark it as a 0. I'll mark it as kind of the null set symbol. There is this little nothing in there, along with a 1, a 2, and a 3. So sure, this null set is a subset of A. So actually, the null set would be a subset of absolutely any set out there. All right? Even if it's the null set. You could even say the null set is a subset, of course, of the null set. So any set that you want to make, the null set will be a subset of it. Okay? Now, a question might be, is this a proper subset? The null set is a subset of A. Is that a proper subset, or is that an improper subset? What do you think? Well, it would be a proper subset. It's a proper subset, right? And it's proper because A has more members in it than are in the null set. Okay? Is the null set a subset of a null set? Is that a proper or an improper subset? And the answer would be it's improper, right? Because they are equivalent sets. One doesn't have more than the other. Okay? All right, so that is the null set, or the empty set. And then finally, let's talk about the mutually exclusive sets. So if I have a set such as, we'll mark this one as M, just to use a different letter. M is equal to the set 1, 2, and 3, and P is equal to the set 8 or 9, 10, and 11. All right? Is M a subset of P? And the answer is no, it's not. So that much we can say. M is not a subset of P. All of M is not also in P. So M is not a subset of P. We could also say that P is not a subset of M. All right, so that much is clear. But there is something else that we could say here, and that is that these two sets are mutually exclusive. Mutually exclusive. And what that means is they do not share any members. There isn't a single member that's shared between M and P. Okay? So these would be considered mutually exclusive. Mutually exclusive. Okay? Now, if I have a third set, let's throw another set in here. Let's call it set Z. And this set is going to be equal to 9, 14, and 15, and 16, let's say. And let's maybe give another one here. Let's give a set V, and this one is going to be equal to a 0, 3, 9. Okay? Now, if I were to ask you, or I should say, are sets Z and P mutually exclusive? So, just so we know, this one and this one. Are sets Z and P mutually exclusive? And the answer is no, they are not. Now, they are not subsets of each other, going either direction, but we should note that Z does have a 9 in it, and P also has a 9 in it. So they do share at least one member. They don't share all members, but they do share one. And so if they do share one, they are not mutually exclusive sets. All right? Now, let's look at the next one. Let's try V here. Is V, or are V and M mutually exclusive? And the answer here would be yes, they are. Or no, I'm sorry. No, they're not. No, they're not. Because, again, they share something. They share a 3 in this case. So they are not mutually exclusive. In fact, if we look at the V set and compare that to the P set, we would also see that these two sets are not mutually exclusive because they both share a 9. Okay? So mutually exclusive means they do not share any members at all. All right? Very good. All right, let's move on. So let's talk now about real numbers. And then we're going to use what we've learned about subsets and apply it to the real number system. So real numbers, we've talked about them a little bit at the very beginning of the year. I think it was in lesson 4 at the very beginning of the year. But we're going to go into them just a little bit more now. So what are real numbers? Well, the short answer is real numbers are pretty much any number that you can think of. All right, so go ahead and give me your favorite number. I mean, that's more than likely it's going to be a real number. So 1/2 would be a real number. 6 is a real number. -12 is a real number. The square root of 4 is a real number. A 0.689432 is a real number. Pi is a real number. 0 is a real number. So pretty much anything that you can give me is going to be a real number. Okay? There are some things out there that are not real numbers, and we have not learned yet. But there are, just so that you know, there are strange animals out there that are not real numbers. In fact, they are imaginary numbers. But anyway, we'll save that for a different day. Right now, suffice it to say that pretty much any number that you give me is going to be a real number. Okay? So, that's a lot of numbers. And we speak to that in the second fact. The real number set is infinite. Infinite meaning it has no end, right? So it just goes and goes and goes and goes and goes forever. Okay, so there are a lot of real numbers out there. Okay, now let's move on to fact 3. It has an infinite number of subsets. So again, if you kind of even though it's infinite, just to kind of get a picture of what's going on, let's say I have a big container here, and I'm able to fill this with all of the real numbers that exist. Okay, so any real number that you give me, it lives in this container. So a half lives in here, a 6 lives in here, -12 lives in here, 0 lives in here, some nasty decimal lives in here, pi lives in here. All of these numbers live in here because this circle that I just drew, I told you, contains all of the real numbers. All right, so that is our set. This is the set of real numbers. Okay, now we could make a subset out of this. And how could we do that? Well, we just need to pull out a couple of the members. So let's call our subset, let's call it A. And let's make A the subset, 0 and -12. Those are the members. And clearly, 0 and -12 are both members of the real number set. So therefore, A is a subset of the real numbers. Okay? Hopefully that's clear. And hopefully then you can also see that I could make infinite subsets of the real numbers. I mean, I just chose 0 and -12. I could have chosen any other two numbers. I could have chosen one number. I could have chosen 10 numbers, 100 numbers, a million numbers. It doesn't matter. I could easily continuously pull out new sets, new subsets of this set of real numbers. And actually there are infinite subsets in here, okay? Because there are infinite members in the real set. So that should be pretty clear and obvious. All right. And then the last thing that we want to just make sure we understand, the real numbers, the real number set is often denoted as this kind of fancy R. Okay. And I know it's a little bit, it doesn't stick out very well here, but it's essentially a capital R. Well, it's not a very good one. Capital R. And then there's kind of this line that goes through it like this. Okay. That is your symbol that denotes the real numbers. So if ever you see this kind of this capital R symbol, know that that is representing all of the real numbers, the real number set. Okay? Very good. So let's move on now. Now let's break the real numbers down into some meaningful sets. So we just said that the real numbers are infinite, and we could pull out an infinite number of subsets from the real number set. But there are some sets in particular that we do use more often than others. And so there are some important subsets that we need to go over. So let's break it down. The first subset of the real numbers is the natural numbers. Okay? So in a way, we can kind of think about this as, at the dawn of time, Adam and Eve looked around and they realized that there were doubles of things and triples of things, and they realized that they could count. And so they saw, whatever it might be, 1 apple, 2 apple, 3 apple, 4 apple, and they just had to come up with a way to verbalize how many apples they were seeing. And so they came up with this number. If there was 1 apple on the tree, well, then we're going to call it this. If there's 2 numbers, we're going to call it, or 2 apples, we'll call it this, and so on, right? So it's just kind of the natural numbers. It's what you would kind of expect to start with. If you're counting something, you really do need to know how to count from 1 to whatever it is that you're counting to, right? And that's what the counting numbers or the natural numbers are referring to. So it starts with 1 and it goes all the way up to infinity. Again, just counting by ones. All right, so pretty straightforward. But eventually, Adam and Eve realized that they had eaten all the apples, and so they needed to somehow say that there weren't any more. All right, and so then they introduced a new number, and that was the 0. Okay, and that brings up a whole new subset to the real numbers. Okay, so we have the whole numbers next. And the whole numbers are exactly the same thing as the natural numbers or the counting numbers, except there's an additional member in the set, and that member is 0. Okay, so now we have 0, 1, 2, 3, 4, and so forth. Okay? And then, as time went on, they began to realize the importance of knowing negative numbers. Okay, and so then they had to introduce this whole concept of negative numbers. And so now we have the subset that's known as the integers. And that includes all the negative numbers as well as all of the positive numbers. The whole numbers, I should say. So it's 0, 1, 2, 3, 4 to infinity, and then all the opposites of those positive integers. So -1, -2, -3, and so forth. Notice they are whole numbers. They are not fractions. So far, none of these sets have dealt with fractions yet. We were just looking at counting numbers, and then we added the 0 to it, and now we're adding negatives to it, but we still don't have any decimals or any fractions or anything strange like that. All right, very simplistic. Okay, so those are your integers. Now, one other note here is that integers are so widely used in mathematics that we do give them kind of another symbol to represent that particular set. And the symbol is this Z right here. It's kind of a big capital Z. And again, sometimes it'll have like a second line next to inside of it. Looks kind of like this. So when you see this symbol, just know that this represents the integer set, or I should really say the integer subset of the reals. Because notice all of these numbers, again, just to emphasize this, all of these sets that we've been talking about, our natural numbers, our whole numbers, and our integers, they are all part of the real numbers. So all of these sets live inside of this real number world right here. Okay, they're all subsets of the real numbers. Okay. And in fact, if you're paying attention, you'll notice that not only are these subsets of the real numbers, but you could also say that the natural numbers are subsets, or is a subset of the whole numbers, right? The natural numbers is a subset of the whole numbers. All of your natural numbers are included in the whole numbers. And the whole numbers have one extra. So you might even say natural numbers are a proper subset of the whole numbers. Okay? And then also, continuing that vein of thought, we could say that the whole numbers are subsets, or is a subset of the integers. Because all of the whole numbers are in the integers, along with some other things. So the whole numbers are a proper subset of the integers. Okay? So kind of make sure you keep that in mind. All right, very good. Those are probably the three most common and most useful subsets for the real numbers. All right, so now we do have two other subsets that we need to get through here, and they are the rational numbers and the irrational numbers. Okay, so the rational number subset of the real numbers are simply any numbers that can be written as fractions. Okay, if you look at this word, rational, you see in the word ratio. And remember, ratio is just a fraction. So 3/4 is a ratio. 1/2 is a ratio. So rational numbers are numbers that can be written as ratios or written as fractions. Okay, so some examples of rational numbers would be things like, 1/2. All right, obviously that's a rational number because it's written as a ratio. That one's pretty clear. So, and then also, what if I have 0.75? Well, 0.75 is a decimal number. However, we could write that as a fraction. That is equivalent to the fraction 3/4. So since we can write it as a fraction, then it is a rational number. Okay? Many other fractions are out there. If I have 0.33333 going on for infinity, is this a rational number? Yes, it is, because it is equal to the fraction 1/3. Okay? So this would also be a rational number. So many, many, many numbers out there are rational numbers. And again, how do you know if it's rational? It's rational if you can write it as a ratio of two integers. Okay, so notice these are all, fractions made up of two integers. How about the number 6? Is that a rational number? Well, the answer is yes, because I can write that as a fraction of two integers, or a ratio of two integers. They would be 6 over 1. That is a ratio of two integers, and it is equal to the 6. So therefore, 6 is a rational number. Okay? And if I go back up to my list here, we can kind of say that, a lot of these numbers that we're seeing, or actually all of these numbers that we've seen so far, all of the integers could be written as fractions. They're just whole numbers. I could easily write those as fractions. All of the whole numbers could be written as fractions. All of the natural numbers could be written as fractions. Okay, and that's actually, if you're catching on to this, you'll note that I'm being a little redundant here, because if I say all the integers are rational numbers, that would mean automatically that whole numbers and natural numbers are rational numbers, because whole numbers are only sum of the integers, and natural numbers are only sum of the whole numbers. So if I say the integers are all rational, that would carry down the ladder here and indicate that all of them are rational. All right. So, but that is what a rational number is. It is just simply any number that can be written as a ratio using integers. Okay. And then finally, irrational numbers. Irrational numbers are exactly what they sound like. They are numbers that cannot be written as ratios. So everything else really is an irrational number. So anything that is not rational is irrational. Anything that is not irrational is rational. You can't have a number that's both of these. It's one or the other. So all of these numbers that we've shown so far are all rational, which would mean that they're not irrational. And the irrational numbers would be things like this. So the square root of 2, for example. I won't go into the proof behind this, but the square root of 2 is an irrational number. I would not be able to write that as a fraction of integers. Okay, if I were to change this into a decimal, actually solve for the square root, I would end up with a decimal, and then I'd end up with numbers that would go on for infinity without repetition. Okay, so these would just keep going forever and ever without repetition. And if you have that, then you know you have an irrational number. Okay, so just to be clear, notice this one up here, this 0.33333, that one goes on for infinity. However, it is repeating. It's repeating this 3 over and over and over and over and over again. And so that is a rational number. But if it is a decimal that goes on for infinity and never repeats itself, that would be an irrational number. All right, so the square root of 2 would be an example of that. The square root of 3 would be another example of an irrational number. Pi is an irrational number. We always think of pi as just being 3.14, but actually pi is much, much longer than that. And actually, pi is 3.141592654, and it just keeps going on and on and on and on and on. Okay, but we usually just worry about rounding it to the nearest hundredth, and we use just the 3.14. But it is an irrational number. All right, very good. Now, let's just real quickly run through a couple of those properties of rational versus irrational numbers so that you've got them in your notebook. So here you go. Here's a couple of facts. All numbers are either rational or irrational. There's no getting around it. It's one or the other. Irrational numbers contain decimals that go on for infinity and do not repeat themselves. We just got done going over that. This is kind of interesting. The product of an irrational number and a non-zero rational number is an irrational number. All right? So in other words, if I take something like pi, which we just said was irrational, and I multiply that by a rational number, let's say a 2, the end result will be 2 pi in this case, but 2 pi is going to be irrational. All right? So the irrational component usually wins out. when we, well, actually, it always wins out when we do multiplication. So you have an irrational number, you multiply it by a rational number, you're going to get an irrational number. Now, you do have to be a little bit careful with this because I could have an irrational number like the square root of 2, and I might multiply that by another irrational number, square root of 2. Well, the square root of 2 times the square root of 2 is actually a 2, and that is actually rational. So if you have a rational, times an irrational, then you will get an irrational. However, if you have an irrational times an irrational, it may not be the case. Okay? An irrational times an irrational could be rational. Okay? So the one to really remember is just when they're opposites. When you have the opposite, a rational times an irrational, the end result will always be the irrational. Okay? Similarly, if you take the sum. So if you take an irrational number such as pi and you add 3 to it, well, the end result is also going to be irrational. So again, the irrational wins out when we have, opposites. So if you have irrational times a rational or irrational plus a rational, you'll always end up with an irrational. Okay? So hopefully that's straight in your head. I don't know if they're actually going to quiz you on these two right here, but they are kind of interesting to know. Okay? Very good. All right, so let's put it all together. What have we learned? Well, we've learned about sets, subsets, and all of the different subsets of real numbers. Okay, or I shouldn't say all of them, but the most important subsets of real numbers. So what I want you to just focus on for a second is this picture. This picture just kind of gives you a visual of what we've been talking about. So remember I gave you earlier, I showed you the circle, and I said, all right, let's pretend all the real numbers are in here. Well, that's exactly what we're doing here. We have, instead of a circle though, we have a box. So we have this outer box here, kind of surrounding this whole shape. That is the container for the real numbers. So all of the real numbers live within this box that you see, this exterior box. Okay, it contains all the real numbers. They all live in here. All these dots might be real numbers, and they all live within. Whoop, that one doesn't. That one doesn't live, and the rest of them, they all live within the box. Okay. Now, inside that box, we have these different groupings. So if we start with the natural numbers, in this red circle down here, that red circle contains all of the natural numbers. So notice it contains 1, 2, 3, and of course going on for infinity. Okay? All of the natural numbers. Now, this whole red circle, though, is contained in this yellow circle. The yellow circle contains all of the natural numbers, and in addition, it contains a 0. Okay? So do you see how the natural numbers are all a subset of the whole numbers? They are contained within the whole numbers. Okay? In like manner, the whole numbers are a subset of the integers, this green circle here. The integers contain the whole numbers. All right? So you could say that, natural numbers are contained in the whole numbers, which are contained in the integers. Okay? And then we could go out even further, and we can say, okay, well, now we've got numbers that are 0, 1, 2, 3, all the way up to infinity, as well as negative 1, 2, 3, all the way up to infinity or negative infinity. And combined with that, we're also adding fractions in there now. These would be your rationals. Okay? So they're all the integers plus plus fractions. Okay? So that would be irrationals. And then finally, we have the irrational. And notice that the irrational is kind of out here by itself. Okay? The irrational, it doesn't mix with the rest of these. It is mutually exclusive. Remember that term, mutually exclusive from these rational sets, integers, and whole and natural sets. There is nothing in the irrational set that is also in a rational set. Or there is nothing in the irrational set that's also in the integers. Okay, they're completely separate. They are part of the real numbers, though. So irrational are real. Rational are real. But rational can never be irrational. Okay, so this diagram kind of lays it out for you and kind of shows you all the different subsets within the real number system. Now, in your book, I wrote that up here on page 249. There is a chart in your book that's basically describing the exact same thing. It's just not as colorful, but it's describing all of these groupings as well. So if you need to refer back to that to study, I would recommend it so that you know which groups are subsets of other groups. Okay? All right, so now let's look at a couple questions here. So question number 1. If I have the fraction 1/3, and remember this kind of this E shape here represents elements, element of, or member of. All right, so 1/3 is an element of what subsets of R, which remember represents the real numbers. Okay, so 1/3 is a member of what subsets of R. So here are all the subsets of R. We see all of them here. In which of those subsets would you or could you find a 1/3? Okay, well, it would be in the rational subset, right? It would be in the rational subset. Do you see why? Where is 1/3 going to live? It has to live in here, right? Here is 1/3. Oh, that looks like 0.3. 1/3 is going to be living in this blue bubble. All right? Because it's not an integer. It's not a whole number. It's not a natural number. It's not an irrational number. It's a rational number living here. So it would be part of the rational subset of the real numbers. All right? How about the next one, number 2? Square root of 2 is a member of what subsets of R? Well, what do you think? The square root of 2. Square root of 2 would be a member of the irrationals. Oops. Irrationals. That's where it lives. All right, so this would be a member of the irrational subset. Okay. And of course, I could, I suppose, in both of these even claim that it's a member of the rationals. It's also a member of the reals. Because remember, the reals is this whole picture. Okay, so it's a member of the rationals. It's also a member of the reals. So maybe I'll put that too. It's a member of the reals. Okay. Because the reals are a subset of the reals. I could say that the real set is a subset of the real set. That's perfectly fine. So it is a member of the rationals as well as the reals. And same thing would apply here. It's also going to be a member of the reals. In fact, any subsets that we talk about, any numbers that I list out here and ask you what subsets are they from, you can always say they're a subset of the reals, at least up to this point, because we haven't learned anything that's not going to be a subset of the reals. Okay. All right, so number 3, -4 is an element of what subsets of R? Well, where does -4 live? -4 would live with the integers, right? Because -4 would not be a natural number. It's not a whole number. It is an integer, right? In fact, whoops, they have it right there. So it is part of the integers. So what subsets is it in? Well, it's in the integers, but now we have to watch out here because not only is it in the integers, but because it's in the integers, it's also in the rationals, right? Because the rationals contain all of the integers. So all of the integers are in the rationals. So this is -4 is in the integers, and the integers are in the rationals, so it's also in the rationals, and the rationals are in the reals, so it's also in the reals. Okay? All right. Now let's go to the next one here. 0 is an element of what subsets of the real numbers? So where's 0? Well, 0 lives in the whole numbers, right? So 0 is clearly an element, a member of the whole numbers. But since the whole numbers are all within the integers, it's also in the integers. And since the integers are in the rationals, it's also in the rationals. And since the rationals are in the reals, it's also in the reals. All right. So kind of the further that we kind of dig into this chart, in order to work our way back out, we have to pass through everything. So if we find something that's in the wholes, well, that means it's also in the integers, it's also in the rationals, and it's also in the reals. If we find something that's in the naturals, so if I had said, another question 5, what about 1? What subsets of R is that a member of? And you could say, well, 1 is a member of, the natural numbers, but that's also found in the whole numbers, which is also found in the integers, which is also found in the rationals, which is also found in the reals. So it's a member of all of those, everything except for the irrationals. Okay? All right? Very good. So hopefully that makes some sense to you. It's pretty straightforward, but I would say make sure that you wrote down all the definitions that we talked about today. And also in your notebook, I would draw something similar to this chart right here, just kind of showing it in a picture sort of a way. Also, you can look at that on page 249 of your textbook. It's all laid out there as well. So, yeah, good luck with this. I think this is where we're going to stop, and we will pick up more on this in later lessons.